Hello friends. So today we will continue with the examples and theorems of Cauchy sequence. Okay, this is the last point of our first unit sequences. Okay, so we have seen one theorem in last lecture that every convolutional sequence is a Cauchy sequence. Okay, now we will see next theorem that every Cauchy sequence of a real number is a bounded. So we have to prove that every Cauchy sequence is always a bounded sequence. Okay. So let Sn be a Cauchy sequence. Okay. So then by definition, for any epsilon greater than 0, so we can take epsilon is equal to any positive number. So for we take epsilon is equal to 1. So for any this epsilon is greater than 0, there exists natural number m such that the difference between Sn and Sm, okay, or we can write Sm minus Sn is less than, where epsilon is equal to 1, so less than 1 for all m greater or equal to the this natural number. Okay. So this is by definition of Cauchy sequence. Okay. Now this inequality is true for all n and m greater or equal to m. Okay. So we can take one of the value may be equal to m because values are greater or equal to m. So in particular, okay. So in particular, we will take this small m is equal to m because we can take any value greater or equal to this capital M. So we can take this small m equal to this natural number m, okay, capital M. So this becomes difference between Sm minus difference between Sm and Sm is less than 1. And since m is greater or equal to m, this is true for m greater or equal to m. Okay. This is true for all n greater or equal to m. Previously, we have written n and m greater or equal to m. But now we have directly taken m is equal to m. So m, this capital M is always greater or equal to capital M, and this n is greater or equal to m. Okay. So this is the condition we get when n is greater or equal to m. Now we know we can write mod of Sn is can be written as mod of Sn minus Sm plus Sm. Okay. Now we can use triangle law of addition or triangle inequality. So this is A, this is B. So mod of A plus B, we know it is always less equal to the mod A plus mod B. This is less equal to the mod of Sn minus Sm plus mod of Sn. This is capital M, this is also capital M. But we know this mod from mod of Sn minus Sm is same as mod of Sn minus Sn because here in mod A minus B, say mod of A minus B is equal to mod of B minus A. Okay. But this is strictly less than 1. So this implies this mod of Sn. Okay. This was less equal this, but this element is strictly less than 1. So this implies mod of Sn is strictly less than this is 1 plus mod of Sm. Okay. And this is valid for all n greater or equal to the m. Okay. So this inequality says if sequence has element S1, S2, Sn up to so on, then all the elements of the sequence are bounded by this element. So all the elements after this m. Okay. So suppose this is the element of a sequence. Suppose S1, S2, somewhere there is say Sm plus 1 up to so on. Okay. Now whenever this n is greater or equal to m, okay. So suppose this is here, there is Sm minus 1 before Sm. Now this identity says, this inequality says that the element of the sequence are bounded by this element. We can give it a name SH. Whenever m gets equal to m. So see, here S is S1, S2, Sm minus 1, here Sm plus 1 up to so on. From here, see, the sequences are Sm plus 1. So this quantity m is greater equal. So this here, that this notation is greater equal to m. Here is m, here m plus 1. Okay. So whenever n is greater equal to m, elements of the sequence are bounded by this quantity. So from this Sm, all the elements are bounded by the quantity h. Now we have to only focus on this previous m minus 1 element of the sequence. Okay. So this implies we can take. So if we take k is equal to the maximum of mod of S1, mod of S2 up to mod of Sm minus 1, and now all the elements from Sm are bounded by h, so their maximum is h. Okay, so the maximum value among these will be the bound for the sequence, because all the elements from this Sm are already bounded by h, and this S1, S2, Sn are real number. Okay, so the elements after this Sm are already bounded by h, and this previous terms has this real number. So mod of S1 may have some real number. Since the sequence is in a sequence of real numbers, all these elements are some real, okay, or constants. So maximum of this is the upper bound for sequence. Okay, suppose if h is maximum among these, then every element of the sequence is bounded by h. If this mod S1 is highest element in this set, then sequence is bounded by this number. So whoever is the maximum in this set will be the bound for the sequence. Okay, this implies our sequence, each element of sequence is bounded by this k. Okay, this implies sequence Sn is bounded. We have proved every Cauchy sequence of real number is always bounded. Now we will do one task. We have about 10 sequences on the board. We have to identify which of these sequence are Cauchy sequence. Okay. Now here we don't have to theoretically prove whether how this sequence is Cauchy sequence or not. We have to just identify. Okay, like we do in the objective examination. Okay, so the criteria for sequence to be a Cauchy sequence in general is very simple. If we know if some sequence is convergent, then it is always a Cauchy sequence. If sequence is not convergent, it cannot be a Cauchy sequence. Okay, so the first example is the sequence whose n term is 1 by n. Now we have already seen this example and we have proved this sequence 1 by n is convergent. Okay, and converges to limit 0. This implies this is the Cauchy sequence because it is convergent sequence. Okay, so this is the Cauchy sequence. Now next example is the sequence 1 minus n square. The sequence whose n term is 1 minus n square. Now we will try to find the limit of n term. You will get infinity because this limit of 1 is 1 minus limit of n square. As n tends to infinity goes to infinity, so limit of n term does not exist and goes to infinity. So the limit of sequence does not exist. So sequence is not convergent. So the sequence is not Cauchy sequence. Okay. Now again similar example, the sequence of natural numbers. Okay, whose n term is n. The element of the sequence are 1, 2, 3 up to so on. Unbounded sequence also tends to infinity. As n tends to infinity, the sequence also is divergent, so it is not a Cauchy sequence. Then the sequence minus 3 raised to power n. Okay, the element of the sequence are look like so minus 3 minus square of minus 3. Okay, so this minus 3 and is outside. Okay, this 3 raised to power n is a is different from, this is not like minus 3 raised to power n. Okay, this minus is attached to the value of 3 raised to power n. So the square of minus 3, so this is equal to minus of square of 3, so 9. Okay, after so again as n tends to infinity, 3 raised to power n also tends to infinity, and this minus, so this sequence also tends to minus infinity. That is, sequence is not convergent. So this is not also Cauchy sequence. So this is not again Cauchy sequence because this sequence is not convergent. Okay. Now the sequence x is to power n. The sequence whose n time is x is to power n, where mod of x is less greater than 1. We have seen the formula. Okay. Limit of x is to power n as n tends to infinity is equal to infinity if mod x is greater than 1, and it is equal to 0 if mod x is less than 1. Since mod x is greater than 1, limit of this sequence is infinity. Okay, so this sequence is also not a Cauchy sequence. Okay, and this sequence x is to power n such that mod x is less than 1 is convergent and its limit is 0. This is the convergent sequence, and so it is the Cauchy sequence. Okay, then this sequence we are seeing, this sequence is monotonic, increasing and bounded. So by monotone convergence theorem, this sequence we are seeing is convergent. This is the Cauchy sequence. Okay. Next, minus 1 is to power n into n. We know this sequence infinite oscillator sequence. This sequence oscillates infinitely. Okay, and this sequence tends to either plus infinity or minus infinity, depending on the value of n. So this sequence is also not convergent, so not a Cauchy sequence. We also seen this sequence, and limit of this sequence you are seeing, this sequence is monotonic, decreasing and bounded, so convergent, and limit will be equal to what we are just find limit. So we will divide denominator by n. So here it will be 1. This will be 1 by n. So limit will be 1. So this sequence also convergent. So this is also a Cauchy sequence. Another example, this is also example we have seen. This sequence also monotonic, increasing and bounded. So by monotone convergence theorem, this sequence also convergent. This is a Cauchy sequence. Okay. So the general idea is every convergent sequence is a Cauchy sequence. If we know some sequence is convergent, then it is always a Cauchy sequence. Okay. So we have already known that every convergent sequence is a Cauchy sequence. Now the Cauchy convergence criteria says a sequence, if it is a Cauchy sequence, then it is a convergent sequence. That is, a sequence is convergent if only it is a Cauchy sequence. So this criteria says if a sequence is Cauchy sequence, it is convergent, or same if it is a Cauchy convergent sequence, it is a Cauchy sequence. If only. So every Cauchy sequence is convergent sequence, and every convergent sequence is Cauchy sequence. This is the Cauchy convergence criteria. Okay. So we have to prove a sequence is convergent. Then instead of using our general definition of convergent sequence, we can use a definition of Cauchy sequence. Okay. If we show a sequence is Cauchy sequence, then sequence is a convergent. Okay. Now we will see example. Okay. In this example, we are to show that this sequence whose n time is 1 plus 1 by 2 plus 1 by 3 up to 1 by n is not a convergent sequence. Okay, so this sequence is not converge. Okay, so here we will use a Cauchy convergence criteria. We will show this sequence is not a Cauchy sequence, so the sequence is not convergent. Okay, so we will prove this theorem using method of contradiction. Okay, so we will first assume. So we assume on contrary, we assume that Sn is convergent. Okay. Now, since the sequence is convergent, we know this is the This implies sequence Sn is a Cauchy sequence. Okay. Since every convergent sequence is a Cauchy sequence and this sequence is convergent, so this sequence is a Cauchy sequence. Okay. So by definition of Cauchy sequence, for any epsilon greater than 0, we can find natural number such that difference between any two terms is less than epsilon after that natural number. Okay. So we will take epsilon is equal to 1 by 2. So for this epsilon greater than 0, there exists a natural number, say m, such that difference between the terms of the sequence is Sm minus Sn is less than epsilon. Okay, is less than epsilon. Then epsilon is 1 by 2 for all n and m greater or equal to this capital M. Okay. Now we will take particular case for the n and m greater or equal to m. So we want the elements which are greater or equal to m. So we will take m is equal, this small m is equal to 2 times this capital M and n is equal to m. So we will get a number which are greater or equal to m. So in particular, we will take this small m is equal to 2 times of this capital M and this n is equal to m. Now m is greater or equal to m and twice m is also greater than m. So both n and m are greater or equal to this capital M. So put this value in this inequality. So what we will get? So what we will get now? So this implies. Now we will take difference between Sm and Sn for this values of m and n. Before that, okay, we will calculate what is the Sn and what is the Sn. So this is the Sn. Okay, Sn contains n terms. So we have S m is equal to S twice m because we are using m is equal to twice m and the term S twice m will contain twice m term because Sn contain n terms and the S2m will be equal to 1 plus 1 by 2 plus 1 by 3 up to somewhere 1 by m plus 1 upon m plus 1 up to 1 upon m plus m, that is 1 upon twice m. Okay. And this term Sm, okay, here Sn where we are taking n is equal to capital M will be equal to the Sm and this Sm will be sum of m terms. Okay, and the Sm will be equal to 1 plus 1 by 2 plus 1 by 3 up to 1 upon m, sum of m first m reciprocal of first m terms. Okay, so the difference S to m minus Sm will be equal. Now see the terms in Sm's sum of this reciprocal of first m numbers. This term is directly here. See 1 plus 1 by 2 plus 1 by m. Okay, so if we take difference between S to m and Sm, this part will be cancelled. So only part remain is this. The difference will be equal to the, and these values 1, 2, 3 is greater than 0. We don't need to take mod here. So this and this get cancelled after difference. So remain only this part. So 1 upon m plus 1 plus 1 upon m plus 2 up to 1 upon twice m, say, or m plus m. Okay, so 1 upon twice m. Now among these m terms, 1 upon m plus 1 is the highest term because numerator is same 1. Here denominator is m plus 1, denominator is m plus 2, m plus 3 up to m plus m. So denominator goes on increasing, so terms goes on decreasing. So 1 upon m plus 1 is the highest term among all the terms, and this 1 upon 2m is the lowest term. Okay, so we can replace this term by lowest term. So this becomes greater equal to. Okay, or we can write strictly greater than. We know this is the highest term, this is the lowest term. So 1 upon m plus 1 is strictly greater than 1 upon twice m. So we can replace 1 upon m plus 1 by 1 upon twice m. Okay. Again 1 upon m plus 2 also greater than 1 upon twice m. We can replace this by again 1 upon twice m up to 1 upon twice m. What we have done, since 1 upon m plus 1 is greater than 1 upon twice m, 1 upon m plus 2 is also greater than 1 upon twice m. So the sum of 1 upon m plus 1, 1 upon m plus 2 up to so on is greater than sum 1 by twice m plus 1 by twice m up to so on. We are these terms, this is the highest term, so this term is greater than this lowest term. This is also greater than 1 upon twice m. So all the terms are greater than 1 upon twice m. When these last terms are equal, otherwise all the terms are here are greater than all the terms are here. So this term is greater than this term. Okay. And now this summation is m times, see now 1, 2 up to m. So these are the m terms. So this sum is taken m times. So this is equal to m times 1 upon twice m. So m and we cancel. This is equal to 1 by 2. So we have, what do we get? So we have get a difference between S2m and Sm is greater than this. This is equal to 1 by 2. But this is the contradiction to our assumption. Since we have assumed that difference between any two terms after n and m get equal to m must be less than half, and we are getting difference greater than half. So this is contradiction to our assumption. So our assumption that sequence is convergent was wrong. Okay. Or what we assume? So our assumption was sequence is Cauchy is wrong. Since sequence is not Cauchy, sequence is not convergent. So our assumption, this is contradiction to our assumption. So our assumption was wrong. And what was our assumption? Our assumption was sequence is a Cauchy sequence. This is wrong. This implies sequence Sn is not Cauchy sequence. Okay. Since sequence is not Cauchy sequence, sequence is not convergent. So we know Cauchy convergence criteria. A sequence is convergent if and only if sequence is Cauchy sequence. That is, if sequence is divergent, it means it is not a Cauchy sequence. Or if sequence is not a Cauchy sequence, then sequence is divergent. Okay. Since sequence is not Cauchy sequence, by Cauchy convergence criteria, sequence Sn is not convergent. Is not. Okay. This is the one of the very important example on the basis of Cauchy sequence. Okay. So using this criteria, you are shown the sequence whose n term is this is not convergent sequence.